Okay, so we've defined addition and scalar multiplication. What we have now is some properties of these operations that we have. These are found in a box on page 802 of your textbook, so if you find it easier taking notes to just copy it out of the book rather than copy it down from here, that's totally fine. I would suggest, though, that you take the time to write them down. Even though some of them may feel like they're super obvious, we're going to talk a little bit about how important they are and why they're so important as we work through them. Okay. So first of all, we've introduced our objects. We're going to have A, B, and C are vectors in n space. So they're all in the same space. Doesn't matter whether that's 2 space or 3 space. Does matter that they are all in the same place. Then we're going to let C and D be scalars, so they're real numbers. Now, I'm following the same notation as the book. I'm not crazy about having C as a scalar and C with a bar over it as a vector, because that could easily lead to some confusion, especially if I just carelessly drop the bar over C, the vector, okay? Totally legal because they're different symbols. I'm going to go with it because that's what's in the textbook. If I were making a choice myself, I would not use the same letters for scalars that I'm using for vectors, just in case I accidentally make the mistake of dropping that bar at some point and that confuses me. Okay. So these properties do have names. As we talk about them, I will point out the names. I'm not concerned that you have those names memorized, although I would suggest that you familiarize yourself with them. Makes it a little easier to talk about the properties if we have their names, but if you ever forget them, you can just sort of paraphrase things in plain English. So for example, here we've got, if I have two vectors A and B, A plus B is the same as B plus A. That's actually the commutative property of addition, and this would be of vector addition because I'm adding vectors. Okay, so the word commutative just says the order doesn't matter. Now, if you forget that name, you can say, hey, when I'm adding vectors, order doesn't matter. Adding this one to that one is the same as adding that one to this one. So you can easily describe it in plain English, but kind of nice to be familiar with the official word for it. Okay. This next property says A plus B plus C is the same as A plus B plus C. I can put the parentheses and group things however I want. That's called the associative property of vector addition. And you might sort of look at those and say, well, why are we bothering to write these down? Because aren't they sort of obvious? I know when I'm adding things, order doesn't matter. Well, the problem is these are true, and they may seem obvious because we're so used to addition having these properties, but we're actually doing something very new. Usually when we talk about addition, we're talking about adding numbers, or maybe adding functions, or something like that. But now we're adding vectors. That's a new sort of object, okay? And just because I call something addition doesn't mean it has to have all the properties that addition of numbers or addition of functions have. Now, if it doesn't, calling it addition might be a bad choice, because if I call something addition, that comes with certain connotations. I expect things like order doesn't matter, and I can group things how I want. I expect to have commutative and associative properties, because I do all the other times I say I'm adding things. So it turns out addition is a good name for this operation that we have, because it does in fact have these properties that are suggested by that name. But we want to be very careful, because we are going to see in just a couple of sections, there's going to be something that a lot of you are going to say, well, that's obviously true, and it's going to be false. Because if you make assumptions just based on the way things are named, you can easily make false assumptions. So anytime we're working with a new object, and vectors are new objects, it's important that we take the time to go through and say things that we might expect to be true are in fact true, or in some cases we'll be saying things that we might expect to be true are not true. Okay. All right. Property 3 says that A plus 0 is equal to A. So the 0 vector is what we call an additive identity. An identity is something where, in this case, it's an additive identity, so that when I add it to something, it doesn't change that thing. Okay. A plus the opposite of A is 0, so A has an additive inverse is what we would call that. And the additive inverse is just denoted as the opposite of A. Okay, 5 and 6 I'm going to sort of look at together. Here I've got two vectors that I'm adding and one scalar. This says I can add the vectors and then scale by C. This says I can scale each vector by C and then add those results. This is a distributive law. This is saying that scalar C distributes over vector addition. Property 6 is also a distributive law, but it's a little bit different. Here, the things that I'm adding are scalars. Here, the things that I'm adding are vectors. If I add two scalars and then scale a vector A, I could just as easily have scaled that vector by each of those scalars and then added those results. Okay, so these are both distributive laws. And if I wanted to distinguish them, I could say scalar multiplication distributes over vector addition, and here I would say scalar multiplication distributes over scalar addition, or over addition of real numbers, to indicate which addition we're distributing over. Okay, property 7. If I have two scalars, C and D, and one vector A, multiplying the two scalars and then scaling A by that product is the same as taking A and scaling it first by one scalar and then scaling that result by a second scalar. This is essentially an associative property as well, although it's a little bit different from this one. Here, with this associative property, all of the objects were vectors, and I was just associating them in different groups. Here I've got three objects. Two are scalars and one is a vector. That's because we're dealing here with multiplication, and with multiplication I don't have to have like terms. Okay, don't have a lot of space here, so I'm not going to write down, but that's another associative property. And then one copy of A is the same as A. If I scale something by one, it doesn't change anything. Not a huge surprise there, but worth pointing out. Okay, all right, so what we're going to do in the next videos is we're going to actually prove one of these things. I'm going to pick property 2, the associative property, and in the next video we're going to do a formal proof that this is true for all vectors. I'm going to prove it for all vectors in 2 space. The proof that it's true in 3 space is very similar, but as you'll see, when we're doing a proof, I'm going to need to go to the component level. And that's because right now I don't know a lot about vectors. Vectors are these new things. So I've defined what I mean by addition and scalar multiplication, but that's about all I have to work with. Okay? But the components of vectors are real numbers, and I know a whole lot of things are true about real numbers. So when I'm proving something about vectors, I'm almost always going to go to the component level so that I can use the properties of real numbers, which we already have established. Okay? So that's what we'll do in the next video. See you then.